And you guys can see my PowerPoint, right? All right, so if you have any questions, just type them on the chat and I'll be able to monitor that. And then let's look at this question that you were to answer. Most of you got the correct answer, which is, in this case, close to 76 solar masses. Sorry. Now, so this is the solar mass, and then the total one, once you convert it to that, is 76 solar masses. For the, just by estimating the masses based on this value right here that we see there, that would be the 300 frequency that was read off this chart. Any questions about that? All right, so with that result, we're just thinking about doing an estimate, and we're estimating based on classical physics, except for one parameter that we needed general relativity, and we didn't discuss how it was obtained, but I don't think I would do that to you guys. You probably need to take an advanced graduate level class to follow all of the general relativity to get that parameter that we estimated. But for the rest, we were just using classical physics, not general relativity. We ended up with a mass that is 76 solar masses based on this value right here. And the actual mass, if you were to use, and this is by using numerical calculations and looking at the sampling the data and using those data points to feed the very complicated general relativity equations, what you obtain is that the total solar masses, the total mass of the LIGO, what LIGO measured based on general relativity is 65 solar masses. So I think that this is very close. I think that that value is pretty close. I don't know if you guys agree with me, but this is awesome, right? That you can see this close of an agreement. 76 versus 65. That was the very complicated equations that, and it's just from reading the value on the data right here, right? Any questions about that? All right, so another thing that could be done from the data is figuring out how much mass was radiated. And the energy radiated during the event right here, so we hear this whoop, that's a lot of energy that was used to generate this gravitational wave that is moving back and forth. Basically moving a space back and forth here, that, and then we see that motion back and forth from the wave passing through us. So that energy radiated during that instant can be calculated too. And the LIGO collaboration figured out that there was, let me write this down. The gravitational radiation generated when the two black holes collided and merged into one, they said that gravitational radiation generated was about 3 solar masses. And this was emitted in about 0.1 of a second. So that's a lot of energy. In just a tenth of a second, the equivalent of 3 suns basically was converted into making a space-time oscillate. And those oscillations made it to us billions of years away, billions of light years away, and basically moved our space, moved us, and we got in one direction shorter by the width of a billionth of a proton. So we could look at Einstein's equation, E is equal to mc squared. So now we have that the mass is about, with this mass, about 3 solar masses. We can stick that in there, and we would get that the radiation, the energy was about 5 times 10 to the 47 joules. So this energy was all radiated in about 0.1 second. So this is from the black hole. So now let's think about the sun for a second. The sun emits energy, right? It's not gravitational, but it actually electromagnetic radiation. And in a tenth of a second, in the same amount of time, it radiates about 4 times 10 to the 25 joules. So you might say, oh, this is a really big number, right? Well, the sun is generating that also in about a tenth of a second. The important thing, though, is to realize that there's an exponential. This is how many, there's a 5 followed by 47 zeros. And this is a 4 followed by 25 zeros. So if we look at those two values, they might look like a lot, but in reality, the one from the black hole merger is not twice as much, right? It's not just double that. It's actually that there's an exponential increase between the two, a huge exponential increase. And to quantify that, if we look at how much energy the sun is going to radiate over its lifetime, so in about 10 billion years, the radiated energy of the sun is going to be about 0.01 of a solar mass. If you convert all of the energy that the sun is emitting over its lifetime, which the lifetime would be between 9 and 10 billion years, I'm just using 10 to round up, and convert that energy radiated, electromagnetic radiation radiated by the sun is basically just going to emit over its whole lifetime, several billion years, less than 1% of its solar mass. Does that make sense? Questions about this? I don't know if this is impressive to you guys as how impressive it was to me when I read and saw this article over here. So we can also estimate how much, we can do our own estimates. And let me change this to blank. Okay. We can do our own estimates with just normal gravitation. So let's do the following. we have orbital energy here, right? So let's estimate the total gravitational energy by using this equation right here. Basically, the gravitation, this is the gravitational potential energy of the two masses when they're separated by their radius, right? We're gonna use that, and we're gonna assume that the black holes were separated, the distance between them is the Schwarzschild radii of them, and let's calculate all that. So let's do it over here. So this is our classical evaluation of the energy radiated. Due to the gravitational wave, right? So we start with that first equation. So this is the total potential energy. And as you know, this is 1/2 G, one solar mass, the other solar mass. And then here you would have, sorry, not a 2, I already have the 2 there, R plus capital R. And then another equation that I have somewhere behind here, let's see. This one right here for the R plus R, capital R and lowercase r, I can grab that equation and bring it over. So let me use the other equation, which is R plus big R is equal to 2G over C M plus little m. And using this second equation on the first one, plugging things in and so forth, I get 1/4 big M, little m, big M plus little m times C squared. Questions? So now, one thing that we have to discuss, this is very similar to the problems that you do in classical mechanics and electrostatics. This is the energy. So we're talking about energy radiated, right? So this is the total energy after, once they got into this distance r plus little r. So for the purpose of the estimate that we're doing, this is the energy radiated by the two orbiting black holes. So we assume that the final separation is this. This is the final energy, right? The potential energy of the system. And we can assume that now we have to figure out when do we start looking at when they started to radiate gravitational waves. So if we assume that there are two black holes coming together, right? They're orbiting each other. When they're separated, the gravitational waves that they're emitting are very tiny. So we can assume that when they're separated, the initial separation is way larger than this distance between the two. And just for this estimate, we can estimate that that distance between the two is going to be infinity. So the initial is going to be exactly the same thing, right? Because this didn't change. These two parameters didn't change. But then this one is going to be infinity because that's the distance between the two. So that's what? Anybody? Arthur, what do you think?
0.
Exactly, right? So once we have this value as 0 and we can calculate this one, the one thing that we haven't looked at is what is the individual masses, right? So we could look at the masses from LIGO. So LIGO estimate so our estimate was 76 for the total one, right? And we could also go and do the same thing for that same estimate for each of them and come up with values. And if we had done that, the individual black holes masses that we would get from looking at when the two are oscillating are 53 and 23 solar masses. But actually, let's not look at those values. Let's look at what LIGO estimates. And LIGO estimated, based on the data, that the big mass is actually 36 solar masses, and the little mass is actually 29 solar masses. So they're about the same according to the estimates that the LIGO collaboration did. So now if we look at the energy separation when they're about to collide, that's when they whoop, do that, right? And just on classical physics, this is the question for you. This is one of the questions for the class. Estimate in solar masses the energy radiated. Okay. Questions about this? How you would do it? Remember, when you put it in here, then you have to compare it to what is the value in solar masses. All right, do I hear any questions from you guys? Is it clear how you would do it? All right. So if we start looking at this plot again, one of the things that we could do when they started taking data, the data before, let's see, can I do this? Can you guys see my screen there? My presentation? I want you guys to see. I want to see if you guys see my mouse. All right, I don't know if you can see the mouse. Let me draw it here then. So if we look at this data, in this area over here, there's a lot of noise, right? So initially, we cannot really tell if we look at this thing, whether there's something happening or not in this area over here. So let's assume that that's noise. Now, if we come over here, around here is where definitely we get a signal. Around this area, we can see this sinusoidal behavior afterwards. And looking at the frequency of that strain, we can start seeing that when the initial signal comes in, it happens to have a 45 hertz frequency. So this is the whoop sound that you hear there. So when it's initially is 45%, and if you were to stick to use that value, at 45 hertz is when the initial inspiralation happens when the two are together and then they're orbiting like that. Around 45 hertz is when it becomes observable that they're colliding into each other. And now, if there were two masses orbiting each other, let's see if I have it over here. Yeah, here's the angular frequency, right? We have two masses orbiting each other. Their angular frequency is 2 pi 45 hertz. And assuming the two values that we have for the masses, we actually could calculate the initial separation. So when they started to inspiral, if we do this, we see that they were about 800 kilometers away here in this position when you start seeing this motion right here. They started at 45 hertz, and that would correspond to about 800 kilometers separated from each other. But then in a very tiny amount of time, like about a tenth of a second, going from here to here, right? It's about a tenth of a second. The thing went from being 800 kilometers away to, if we look at the combined Schwarzschild radius, this distance right here that we can also calculate given the masses of the two black holes, they collided together when they were 100 kilometers away. So basically that R plus big R is 100 kilometers away. And that's again, estimating with just classical physics. Any questions? So what I wanted to talk about next is that we're looking at Newtonian physics, and we're basically getting a really good agreement with fully relativistic treatment used by the LIGO collaboration. We did some simplifications and we ignored some things that happened there. Like for instance, the black holes are supposed to spin. So we assumed that the black hole was this featureless thing, but according to general relativity, the black holes are spinning. And yeah, it's hard to tell, right? And hard to imagine, how would a black object, how would you be able that there's a spin on it? But it turns out that the spin of the black holes is gonna give you some forces between the black holes acting on each other when they're inspiraling into each other. We also have, for instance, this spinning acts on satellites on the Earth, and they can be important because if you don't account for for satellites that are in space, when they're rotating around the Earth, they could change the way that they're pointing at Earth. And if it's like, for instance, a communication satellite that it has to join two parts together, you want to control exactly where it's pointing at. And that's why they carry gyroscopes with them, so that they can reposition themselves so that they're not pointing at the wrong position and sending the signal a different way. So we could look at it and see how these approximations were only corrections. But I think that being so close with classical physics is really awesome. And you don't have to learn about all of the complicated math that you would need for looking at this data. And we can see some of the things that happen. Another thing I wanted to talk to you is how impressive it is that this was measured. It took about 60 years of efforts to get to the size, to the measurement possibilities of gravitational waves. The biggest issue is that you have to measure something, the compression of space. And what they did is that they put lasers two arms of lasers really far away from each other. So they put two lasers, they're far away from each other. One is pointed in this direction. So we have a mirror right here. This is a mirror. Then there's another mirror right here. And then a laser got sent in both directions from here and from here, the same frequency of laser. And when the laser comes back bouncing off the mirror, there's a detector here. And that detector can look at the two incoming beams coming back together. And if the length from here to here, and let me call this one length 1, and the length from here to here, let me call this one length 2. If length 1 and length 2 are the same, then the laser comes back with the same phase as he was sent in for the laser. And there's no, there's constructive interference. Now, if all of a sudden one of them shrinks and the other one gets longer, then the phase, the distance that the laser is passing through, that would be the space length that the laser is passing through, would change, and the two waves coming back, when they get back together, they interfere with each other. So you see this, and the reality is that this L's, the L value is around 4 kilometers. And the change that happened, that happened in one direction versus the other was on the order of 1/1,000,000th of the radius of a proton. So a proton is 10 to the negative 16 meters. So you see this is 6 and the 16 add up. And so this is a 0.22 zeros and then a 1. That's how tiny a change in the length of space was measured by this collaboration. Yeah, so you have a laser. So let me go over the schematics of this. So you would have a laser right here, a very strong laser that sends the light in. And then actually here, there's a detector, but there's also a splitter. So something optics that makes it so that the light goes in this direction and in this direction. So for instance, if you have light going in this direction, you can have, how would I do it? Yeah, like this, sorry. Like a splitter of the light. So the light hits this point right here, and some of the light, the same light goes in that direction, and half of the light goes in that direction. So that just splits the beam and redirects half of the beam in the north direction, half of the beam in the east direction. So once you have that, the light goes and travels all the way across, hits both of the mirrors, and then comes back. And then you have a detector right there that can see when light comes in from the two lights interfere with each other or not. And at that point, the detector is able to tell how much light intensity you have. If they're interfering, the mirrors are placed about 4 kilometers away from where the detector is. And then all of this is encased in a huge tube there's a tube right here, like this, and in that direction too. There's tubes, giant tubes, so that nobody, and it's underground, so that nobody can mess around with it. Finally, the two mirrors are hanging in space with a bunch of setups, like a bunch of pendulums next to each other, to avoid getting the noise of, let's say, a truck was passing by or somebody. I mean, this is so sensitive that it can detect earthquakes that are super tiny. The earthquakes produced when a truck is passing by, when somebody is walking near the detector or anything like that would be detected by this. So therefore they have that the mirrors are hanging from different penduli so that those waves don't affect it. They're isolated. They have like a spring, springs like your car and hydraulic springs, but they have more than just one. They have a setup which is really complicated, where you have like three of them on top of each other to reduce vibrations. And then they're hanging, all of this is on a bar, and then the mirrors are hanging from two different pendulum-like thing so that all of the vibrations don't affect them, all the vibrations on Earth. And then they repeat the setup all the way up, both in Louisiana and in Washington, the state of Washington. And they have the same setup in both, so that the only way that you can tell that there's a gravitational wave signal and not something else is that they both measure the same thing. So do you have any other questions about the setup? So the purpose was to figure out whether we could measure gravitational waves or not. So the gravitational waves were predicted by Einstein in 1915. And people were trying since then to measure these gravitational waves, but they could never measure them because they don't have the right sensitivity. So for the last 60 years, yeah, about 60 years, like in the 1960s is when people started doing really good experiments and finding that they couldn't find the gravitational waves coming at us. So the most complicated thing is that the size of this system, which is 4 kilometers, the change in length is about a billionth of a proton. And they were able to measure this, right? The other thing was that this proved that general relativity was correct in several of the things, because this data right here agrees so well with the theory that we have seen in general relativity. And actually would agree too with some of the observations that we have from Newtonian physics, right? If we just take some of those values in. One thing that is fun, I actually know some of the people that did the experiment. We had one of them here at OSU. So it turns out that the day that they did this measurement, this guy goes to, so they have the experiment running for 24 hours, right? And they have people inside of the experiment making sure that things are working and saying that the data is being collected correctly, that everything is working. So one of the guys in the Washington experiment, he went to sleep. His collection time was over, goes to sleep, and then he goes back, he wakes up, and so he finishes his shift, goes to sleep for the night, and then he has to come back for the next day for the next shift. And it was during his sleeping time that the measurement happened. And he was so excited about it, but I think that he was also a little peeved that it was actually when he was sleeping that he wasn't the one actually taking the data. he could have been, right? Like he was just off by a shift. And another thing is that they actually didn't intend to do the measurement. The measurement happened, they knew that they reduce the amount of noise that they were detecting. And every reduction on noise, like you have noise detection limits, and then you have your actual wave happening. So basically this wave, the strain that is seen here, this strain, they didn't know how big a gravitational wave was going to be, how big of a strain it was going to put in the system. The smashing it together and extending it in the other direction, right? So they actually didn't know how much sensitivity they needed. And they assumed that they were still a few years from getting to that lower and lower sensitivity. But they were going to test the new electronics that they had just put in and do a run for a couple of months, then shut it down, and then do another run after another update. So it turns out that this measurement is made, and exactly when they turn it on September, I think September 7 is when they turn it on to do a couple of weeks run. And on September 14, they see this data coming in. And it turns out that this is the first observation that they have, but it's actually a really good observation because having the two masses were about, so let's go over here, that the two masses were so close together made it so much easier for the data to be collected. So think about it this way. If you have that one of them was 65 solar masses and the other one was 10 solar masses, then you have a big one and a little one, right? And then the big one just hits the little one and there's not as much of a ring coming out. But here you have two guys that are about the same masses, 30 and 30, and they collided together. And because they're so big, they were orbiting, they're both comparable in size. And because they were orbiting together, that's when you see the ring down. And that's really important and serendipitous that it happened because that's why the data is so good. If you were looking at the similar masses, then the data wouldn't be this good. But this one was amazing that the data was this good. And then one final thing is that now they have found the same collaboration. So this is two apparatus. One is in the state of Washington, one is in the state of Louisiana. And if you were to look at this one side first, that means that the gravitational wave was coming in that direction because this one side a few milliseconds before this one. The gravitational waves have to travel at the speed of light. So therefore, if these two sides are separated by a distance of a few thousand kilometers, right? Then there's a milliseconds, I think it's 7 milliseconds from Louisiana to Washington. So for this thing, there's about the detectors are, let's say, 3,000 kilometers away from each other. Louisiana side first, and then there's a shift of 7 milliseconds, and then Washington ceases then. And they were able to see this. So because of that, this one sees it first before this one, then we know that the gravitational wave was coming from that direction. After this two detectors, there's a third one, and the third one is located in Italy, and it's called the Virgo project. So now LIGO and Virgo work together, and now you have three detectors in space, in the Earth, right? So there's one in Washington, one in Louisiana, and then one over here in Italy. And when a gravitational wave happens to pass by the Earth, which it looks like it happens often, not every day, but it does happen often, that means that the tree can triangulate the data and see where the gravitational wave is happening and forming together. So this is actually really cool because now what's happening is that as soon as there's an event, the event could be that two black holes collided together, like in this case. There's actually other things that can happen. For instance, you can have huge neutron stars colliding with each other, and they also generate gravitational waves because they're so dense. Neutron stars colliding with each other or any other thing. And because you can triangulate where the signal is coming from, you have the ability to point regular telescopes in that direction too. And people are doing that nowadays. So there's gravitational wave astronomy. People can point at things with telescopes like the Hubble telescope or any other light telescope. You can also have infrared telescopes and so forth. And they're able to tell if something is happening, point your telescopes in that direction because maybe you can see it in any of the other spectrums. So gravitational waves and light, infrared, UV light, X-rays, everything in the electromagnetic radiation can be observed. And if you have, let's say, two huge objects colliding with each other, in this case, they generated a lot of gravitational wave energy. They might also be sending out X-rays or gamma burst or something like that. And this is like there's something called binary pulsars. And I think that one of those was seen with gravitational waves and with um, actual telescopes. So those would be stars that are sending gravitational waves, but they also send a pulse of light in two particular directions, but they're oscillating like this. So when we're on Earth and we see it's pointing in that direction, it's dark, but then when it's rotating like this, and then it's pointing in this direction, we get to see it and we see it pulsating. So that's what a pulsar is. And people are using all of this to look at the sky, and very exciting things are happening. All right, so let me go back, and this is the question that you're looking to see. Estimate how much energy was radiated. Okay. So with that, I want to ask you if you have any other questions. I hope that you like this LIGO experiment as much as I do. If you want to discuss anything like that, um, you're welcome to come chat with me if you're interested in it. If you guys don't have any questions, then that's the end of class for today. Thank you.